Okay, so let's try a few different gravity type questions, expanding on the FG type stuff we've been looking at. So here we got the Sun, and here we have Neptune, and Neptune's got a mass of about 1.02 to the 26 kilograms, and there's a force of gravity between the Sun and Neptune, which would be about 6.65 to the 20 newtons. And we're just going to start something, just do something basic here. We're just going to find out what is the distance between them. We're going to find the radius of Neptune's orbit. Now, of course, it's an ellipse, so the orbit always changes, so it'll be like the average radius of the orbit. Okay, well, this is just straight up force of gravity is equal to G(m)m) over r squared, and we're just looking for the r. We've got the mass of the Sun from your table of values and stuff like that. Neptune, there's the mass right there. We have the force. So we're just looking for the radius. So the radius will just be the G(m)m) over fg, and then do not forget to square root it, otherwise you are going to be way off. So we have all our values, we can put them all together and calculate that radius. So if we do that, don't forget the square root, we will get an orbit radius of about 4.5 times 10 to the 12 meters, and of course that would be from center of mass to center of mass, but again the radii of the actual Sun and Neptune would be irrelevant, insignificant compared to the distance of the actual distance between the actual surfaces. Alright, well, let's get these things out of here and show you something else. One of the most common things that the force of gravity is often connected to is one of the main things that actually causes things to do, and of course that is orbit. That is the reason why things orbit in the first place. If you've got a planet of some kind and you've got an orbiting object around it, like a moon or something like that, or a satellite, of course this thing will orbit around the initial object. And of course there's a force of gravity between the two. Well, the force of gravity is what keeps it going in a circular orbit. So Fg is often connected to Fc. And of course it's not a circular orbit, but we can take like an average radius, an average v, an average everything to get a general idea of what's going on. So we can actually connect force of gravity to Fc. Now if you actually look at the expressions, Fg of course is G(m)m) over r squared, and this creates circular motion where you'd use the lowercase m, the small, well I would use lowercase m, it's the mass that's actually going around. It's kind of neat because those two m's, first of all, cancel out. So it shows that the actual mass of the orbiting object has nothing to do with the actual orbit itself. It's more about the radius and the speed. So even if we look at the radiuses, one of those r's cancels out, but we're still left with an r. So an actual orbit, where an orbit actually exists, is totally dependent on how far away you are and how fast you're going, in the combination of those two. The mass of the actual object has absolutely nothing to do with it. So it's kind of cool. So just by doing this, we can sort of summarize. You have Gm over r is equal to v squared. We could use this to calculate how fast an orbit is, or the radius of an orbit, and all depends on the positioning as well as the actual main source gravitational mass, the main one, the core one. That actually is really important. So you can actually calculate different things. So it's kind of neat that way. So let's take something really, really simple. Let's say this is the Earth, and this is our actual moon, and let's find out how fast the moon goes around the Earth. Well, we can use this expression right here. So the v of the moon would just be Gm over r, and then you'd have to square it afterwards. And this mass would be the Earth mass, because the mass of the moon actually canceled out over there. So we have the g, that's the 6.67, negative 11. Mass of the Earth is from your table of values. The distance between the Earth and the moon, that is also in your table of values. Put them together, square root it. Don't forget the square root. And you can find how fast, approximately on average, how fast the moon is actually going. So if we put those values in, we'll get a speed for the moon around 1,020 meters per second. So that's how fast approximately the moon on average is going around the Earth. And if its radius would change, if the radius got smaller or bigger, it would affect the V, and vice versa between the two. And of course, if the mass of the Earth changed, it would have to compensate as well. So it's kind of neat how the mass of the actual orbiting object is irrelevant, and that's why satellites can be in orbit around the Earth, because the mass of the satellite really doesn't matter. It's about the positioning, how far away it is, the altitude of it, as well as how fast it's going. Those are things that actually kick in really nicely. Okay, so let's look at something similar. Let's look at a similar type of question. Let's come up with a new planet here. Let's go with a nice orange planet. Okay, so here we got an orange planet, and let's do something really similar. Suppose we got a mass of some kind orbiting the planet, and let's say the planet over here is 9.1 times 10 to the 27 kilograms. Okay, and let's say our little guy over here, let's say it's going 1750 meters per second. Let's just do a little division. There we go. And I want to find out what is the radius of the path. Okay, first of all, you don't have the mass that's going around, but again, it doesn't matter. Now, when we're doing solutions for this, you still want to do proper solutions. Don't just jump to a derivation like this. You still want to start with FG is equal to FC, GMM over R squared equals MV squared over R. It's really good to start like this. Generally, it's really just sort of when derivations come up later on or other steps come on later on, you want to show where the expression comes from. So this is just a derivation between the two. And then once we do that, the radius would just be, well, we're solving for this R down here is what we're doing, so we can switch the two around. That would just be the GM over V squared. And I got the G, that's my constant, the mass of the main object planet, I know that, and then the V is the 1750, and I can square it. Okay, so we put those values in, and we do that, we will get about 1.98 times 10 to the 11 meters, and that would be the radius of the orbit. Okay, so this is just a nice little application of using FG with this type of stuff to find and the radii and speeds of orbits, good old circular motion type stuff. Okay, so let's try another one. Let's go to that. Delete. Okay, so here, let's use this. So here's the Earth. Here, I'll make the Earth a little bigger. Let's make it bigger. Let's make it, all right, there you go. That's a little better. Ooh, kind of chunky, but that's okay. All right, and let's have the, here's the, the International Space Station. Here we have the ISS, which of course orbits the planet. Okay, now to go around, it takes about 90 minutes in order for the International Space Station to actually orbit the actual Earth itself. And it's going around, give or take a little bit, it's going around 28,000 kilometers per hour is how fast it's actually going. So what I'd like to know is how far or how high is it above the surface of the Earth actually as it goes around. Okay, so this we can use some of our circular motion ideas and the gravity ideas in order to figure this out. Now, first of all, I got to change a couple things, adjust a couple things. First of all, this 90 minutes, this would be the period of the orbit, and of course, I want that in seconds. So that would be 5,400 seconds. So I've got a period. I'm going to change this, of course, into meters per second. And that would be like 7,800 meters per second right there. Okay, so now that I have this, I've got time and I've got distance to go in a circle, I can find speed. So this kicks back to your circular motion stuff you guys did. So speed is 2 pi rf going in a circle, or 2 pi r divided by the period, which is basically a variation of dTV. And we can use this to calculate the radius of the orbit. Because we have the v and we have the period, we can find the radius of the orbit. And if we do that, we'll get about 6.69 times 10 to the 6 meters. Okay, so that radius, though, that is from the center of the Earth, but I don't want it from the center of the Earth. I want that little height right there. So that total radius is from where the space station is all the way to the middle. So the height would then be that radius that I just found, subtract the radius of the Earth. So if I do that, I'll get about 310,000 meters. So it's about 310 kilometers, about 300 kilometers above the actual surface on the Earth on average. Okay, and this is how we can apply some of the circular motion stuff to the orbit type stuff you guys have been working on. Okay, well, let's try one more scenario. Here we got the sun. Let's say here we have Pluto. And Pluto's got a mass of about 1.31 times 10 to the 22 kilograms. We'll see if we actually use it or not. We'll see how things go. And we're going to find out a couple things about about Pluto. But you know what? Let's just start with one thing. What is the period of the orbit? So how long does it take for it to go around the actual sun? Okay, and we can figure out a couple things about what's actually going on here, and we'll piece a few things together and see if we can get to the period of the orbit. Now, Pluto obviously is a lot farther away. It's actually about 40 AUs, or astronomical units. If you remember that from grade 9 astronomy, it's about 40 AUs, or 40 times farther away from the sun than the Earth is, and that gives us about approximately 6 times 10 to the 12 meters as its radius. Okay, so let's see if we can use this in order to figure out a few things. Now, first of all, I'm going to try and find out how fast it's going. It's going to come in handy. And I know that FC is equal to FG. We've done this before. And if I put those things together, I can get the expression I had before, which looks something like this, which I can then use to calculate how fast it is. And of course, this mass, this would be the sun's mass, because the mass of Pluto actually cancels out, so we didn't actually need it. So then if I punch the things in, I got the G, the M, and the R as well, find out Pluto's going around 4,700 meters per second on average. Okay, well, now that I have that, period is just time. So I'm looking for period, and that's basically just dTV. So the distance would be the 2 pi r, the circumference of the orbit, divided by the v. So I've got the 2 pi r, I've got the radius, I've got that. I found out my v, so if I put them together, I can calculate the period. All right, so putting those values in, we've got about 8.0 times 10 to the 9 seconds, which of course is a really, really long time. And you know, it's the basic time conversion. That's still going to be about just over 2 million hours. So it's a really, really long time. It takes a really long time for the Pluto to obviously go around the sun being so far away.